So John is here. John will take you forward with the hands-on session.
Thank you, sir. Thank you, ma'am. So, participants, I will be sharing one file in the chat. If you see, you might have just got it, oilerbubble new.zip. Okay, so here we have already set up the case. I will go through the file once and then we can run it. Okay, can you please download and extract this file in the run folder like you have done previously? So I have copied that folder into my run folder. Kindly do that, please. Once you have done that, we can go ahead. As sir has sketched, we can see that our domain is similar to the one that we did yesterday. So yesterday, some of you were having some problem in understanding the domain. I will quickly go over it again. So let me open this in the terminal. Okay, so I will just run blockmesh and I will visualize it. So here what we have is we just have one block with mesh inside it. So now what we are going to do is, as sir said, that certain region we are going to declare as, say in this case, air, because our whole domain will be water and certain region will be declared as air. Now, how we do this? So yesterday, Viraj was showing to you, right? So what we are going to do is use a set fields, right? This is our 3D geometry, if you can see over here. So using set fields dict, this cylindrical region will denote that as air, and the region this this region on top that will declare as air. The rest remaining will be air, will be water. So I will after this I need to run the set fields utility, and once set field is run, then you will see the difference. So right now we have nothing. Just let me run set fields. I will also go through the set fields dict once, but let's first visualize it. So now if I do alpha dot air, you can see the region on top is air, the region in blue is water, and the region over here is again air. So this is how we have set it. Now let me go to set fields dict so that you will understand now what we have written in the set fields dict. So if I open my set fields dict over here, if you see throughout, by default, throughout the whole domain, we are declaring alpha dot water as 1. That means the whole domain is of water and the air fraction in the whole domain is 0. Now, in certain regions, right, where we want the, say now to say a bubble, or this is not exactly a bubble, but the region with air, we are declaring we are calling region as cylinder to cell. That means all the cells that come within this cylinder, we will assign them values as alpha dot air as 1. That means we will assign them the region to be air. So how do we do that? To do that, we specify 2 points, P1 and P2. So those points are nothing but the center points of the two circles. You see one circle on the front face over here and one circle on the back face. So as Biraj was talking about it yesterday, to define a cylinder, you would need 2 points: the starting point of the cylinder, the ending point of the cylinder, right, and the radius of the this cross section. So that we are specifying over here. So the starting point, the ending point, and the radius, and all the cells that lie within this region. In those cells, we will assign alpha dot water as 0 and alpha dot air as 1. That means those whole regions will be now air. Similarly, the region at the top, right, there also we have added here. The region at the top, there also we have added air. So how we do that? Those regions will be selected by the utility box to cell. Now all the points lying within this box. So now what this box is, so this box is nothing but, to define this box, we need to specify 2 points. One is uh, any corner. So this is one corner, and the other will be diagonally opposite corner at this end. So that we are calling it as a minimum and maximum limits. So that is what we'll be defining. So that is after we do that, and when we run set fields, this is what the system does. Other important thing to know is if you would have seen in your zero folder, we have alpha.water.orig and alpha.air.orig. uh, So OpenFOAM uses these files and generates alpha.water and alpha.air once the setfields utility is run. So we need to keep these original files because if I open this, here all our boundary conditions, whatever are needed for solution are given. And if you see this alpha.water, then it gives a list of the internal field where alpha.water is 0 or 1. Right? In this case, where alpha.water is 1. So all our boundary conditions go to the end. Right? So to have an original copy of that file, we name it as alpha.water.org. Now, block mesh is same as what we have seen yesterday. Hmm. PRGH and U and PRGH values also remain same. Now, what is different in this case as compared to the previous one is now in the constant, you have to specify something called as phase properties. So now if I go to phase properties, in the phase properties, we need to specify what are the two phases. In this case, the two phases are water and air. Hmm. And for water, what is the diameter? So our diameter we have assumed to be constant, and we have given the value of the diameter as 1. Okay, because in our case, the water is kind of like the continuous phase, and air is the dispersed phase. So we have given a large value of d for water. And air, again, we are using the constant diameter model. So the diameter of the air particles or air bubbles we have given as 0.3 mm. Then we have something called as blending. Now, blending will be used for, this will help the solver decide in which region do we have a continuous phase, in which region do we have a dispersed phase. So if your alpha is between 0.3 and 0.7 for air, hmm, then that region will be called as a, what you can say, mixed region. If it is less than 0.3, then it will be dispersed. If it is greater than 0.7, then it will be continuous. And then according to this, the various drag models that are there, that will be applied. Along with this, we are defining the surface tension between air and water. Now, interfacial compression coefficient, like you had seen yesterday, C alpha value, right? If C alpha is 1, that means we are applying interfacial compression, and our interface will be sharp. If it is less than 1 or 0, then we are not applying interfacial compression. Now, as Sir was saying that there are many drag models. Over here, we are using the Schiller-Newman drag model for air in water and both water in air. And for air and water, we are using the segregated model. Now, you can go ahead and look at what these models are in detail. I will quickly show you like what is a Schiller-Newman model. So to see that, you can go to your browser. So I'm showing you this so that you can also search for yourself if you find any other model and if you want to use that. So type openfoam.org, right? And in resources, go to C++ source guide, click on say version 9, which we are using, and search. The search option is in search. I will be typing Schiller-Newman. Okay, so you see the Schiller-Newman, everything related to Schiller-Newman pops up. Okay, so what it is, we can go to the source file, the .c file. You'll see the execution over here. Okay, so if you look at it at the bottom over here, for Schiller-Newman, the drag is calculated based on the RE. So now uh, the equation is something like 24 into 1 plus 0.15 RE raised to 0.67 for RE less than 1000, and for RE greater than 1000, it is something like 0.44 times RE. So you can look this up. In some cases, they would have also specified what is the what you can say resource for this. So you can read up more on what that drag coefficient is and how it computes drag. And as sir has already mentioned, the RE is based on the diameter of the dispersed phase. In this case, the air. Yeah. Okay. Yeah. So that is done. So in this case, we are not modeling lift. The aspect ratio we are considering to be default, that is 1. We are also not modeling virtual mass, heat transfer, phase transfer, wall lubrication. So what are all these things? So virtual mass means if there is a relative acceleration between the fluids, then some force that is corresponding to this virtual mass will be added. If we are considering heat transfer between the phases or phase transfer, they have to be added here. Wall lubrication is what happens if the bubble goes towards the wall and how it should react. Hmm? That or any particle goes near the wall, then what it should do. And last, turbulent dissipation is uh, how the bubble will interact with the, or bubble or particle will interact with the turbulent eddies. So all these things you can add depending upon your requirement. After the end of the session, I will share certain resources with you so that you will be able to, go through this. Okay, so this was our phase properties files. Next, in transport properties, we specify what is the what you can say equation, what are the density and various properties. So this is same as what we had done yesterday. Now let me go ahead and run the simulation. So because what you can say the time required to run the simulation is a little bit more, and to reduce that, I have used the decomposed pardic, and I have given 4 number of domains. So I am only using 4 processes because I saw that generally people on an average are having four and above only. So I've given 4. If you have more, you can increase this and make it 8 or whatever. But if you leave it 4 also, it's fine because with 4, the runtime is it's very less. So now open this in your terminal. I think I've already opened. So the first thing that you need to run is block mesh. So I've already run block mesh. After block mesh, once the mesh is created, we need to set the fields, like where in what regions will air will be there, in what regions water will be there. So that also I have done. So for you, you run the 2 commands, run block mesh and then run set fields, which you had already done previously. After you do that, run decompose part. So it will decompose the domain. In my case, it is decomposing it into 4 processes. Now, once this is done, we need to run the simulation in parallel. And if you remember, the command to run simulation in parallel is mpi run. Then you specify the number of processes by the keyword -np4, that is 4 processes, and then the name of the solver. So our solver is multi-phase Euler foam. So name of the solver and then the keyword parallel, indicating that we want to run the simulation in parallel. So Biraj has typed the command in the chat. So if you are having any difficulty, you can copy the command from the chat. So again, I will reiterate. So first will be block mesh. After that, you have to run set fields, and then you have to decompose. Don't change the sequence. After set fields, then you decompose, and then run the simulation in parallel. It will take around 2 minutes, 1 to 2 minutes to run. Yes, so Mr. Prabhu, if you are having a few slots, you please check if you have 4 processors. If you have less than 4, so if you have only 2 processors, make that decompose part the number of subdomains from 4 to maybe 2. So now once we get this solution, see yesterday somebody ran ParaView after this or Parafoam after this, and you were not seeing the results because what you had missed the step of reconstructing. So you have to reconstruct the results. So you have to run the reconstruct part. So after that, we have got our results. Now I will run the command Parafoam. And if I click apply, and from here, I want to see the phase fraction for air. So you see, to begin with, air is at the bottom. As I'm clicking, we see the air molecule or the air region. Now, in this case, the difference is this is the air region and not a bubble. Okay, it is going up and it is mixing with the air at the top. So this is the result that you are getting. Now, if you have this, you can try something. You can try changing a couple of parameters. Like let's say go to not zero. Go to system constant phase properties, and maybe this interfacial compression that is there, maybe reduce it a little, make it 0.1, 0.2. This is something that you can try, but you can try that on your own little later. What I want you to try is, see, yesterday Biraj gave you an assignment to reduce the height of the water column and then run the simulation. Today, what I want you to do is, I have given one region, okay, where there is bubble in only in one region. Instead of that, what I want you to do is do something like this. If I have that, I want you to simulate something like this, right? Keep one bubble above and one bubble below. The dimensions have been given to you. So the center of the bubble is 5 mm from the bottom. The radius of the bubble is 1.5. Okay. I am not too specific about this. You can give maybe 4 mm and 4 mm and maybe give diameter as 1 mm, 1 mm. That is fine. No? But just try doing this. Hmm? This is so that you understand what changes you need to make and in what file. Okay. So
The result shown in Paravi is similar to VF approach, right?
yes, what will happen is if you keep reducing the diameter of the dispersed phase, right? Then what will happen? This bubble, when it is going up, hmm, it will also try to. What will happen is it will kind of diffuse. It will not remain intact as one bubble.
Okay.
Okay, that is also something that you can try a little later. But when we are simulating, what you can say, fluidized bed next, you will be able to see that. So try this now. Try setting two bubbles one above the other and see what result you get. So you should get some interesting results. Can anyone tell me what will be the approach to do this? What you need to do? It is not as simple as yesterday's. Yesterday you had to only edit one value. It is little bit more difficult, but not too difficult. So first, let me ask: have you finished the previous simulation? Can you reply in the chat?
No, sir, it is running.
Okay, it is running. So in the meantime, can you tell me? I will show the set fields dict so that then you can tell me what are the changes that need to be done in case you are running. So let me go to my system and then set field dict. Yeah. So
Hello,
this
sir.
is your set field dict.
Hello, sir. Can you explain once more that like phase properties file?
Okay. Yeah. So 1 minute. What is the error somebody is getting? Okay. Okay. Yeah. No, once you reduce the number of domains, then in that MPI run also you have to change the number. Yeah. So I will explain that again. So in constant phase properties, yeah. So we start with what we have to first specify what are the different phases. In this case, we have water and air. Okay. Then, like what is the phase model? So we are going to consider the constant diameter model. So we need to specify the diameter of the phase. This will be needed to calculate the drag force, right? So because water is a continuous phase, we have given a diameter of 1. Air is a dispersed phase. We have given a diameter of 0.3 mm in this case. And again, we are considering the diameter to be constant. You can change this model to make it maybe, there are some different models like isothermal, where there are models in which the bubble, the diameter will change depending upon the region pressure and all those things. Those models are also there. You can try finding them. So one way of finding that is, I'll quickly give you a hint. So what you can do if you want to know what are the various diameter models available is you remove this constant, add maybe something like say banana No, just for the namesake. So what will happen is OpenFOAM, when it reads this file, it will throw an error saying that banana is not defined. Instead, the available models are, and then it will list, say like constant model, isothermal model. So you will get a list of all the models that are available. This is a quick way of finding it out. And then you can search and read up on those models and see which one suits best for you. Okay. Next is blending. Now, blending will be needed, say, in cases where you cannot distinguish between which one is a continuous phase and which one is a dispersed phase. So here, what we are saying, if say your air is or concentration of air is greater than 0.7 or less than 0.3, then it will either be dispersed or continuous. In anything in between, it will be mixed phase. Next, we are specifying the surface tension. Okay. So surface tension, we are specifying it to be constant and a value. Now, interface compression is similar to what we did yesterday, right? To make the interface sharp. Now there are drag models. So for drag, there is like, if air is the dispersed phase in water, then you are using one drag model. If water is the dispersed phase in air, then you are using another model. And if both of them are like kind of mixed, then you are using something called as a segregated model. Now you can read up more on this. I showed you how to search. You can go and type the name in the source code and look at what is written over there. So you'll get more idea about that. Also, at the end of the session, I will share some resources online which are available. Wolf Dynamics is a good place from where you can get very good information. They have lots of what you can say tutorials, as well as they have explained all these things. But if you want to understand any model in detail, you will have to read up literature and you will have to understand the source code, because everywhere you see, people will just give you few hints as to what it is, but the applicability and when to use which model, for that you have to go through the literature. Then we have lift, aspect ratio, virtual mass, heat transfer, all these things. So you can model all these things as well, right? If you see that lift may be significant, add lift. If you see that the diameter of the bubble is not constant, like your particles are not the same size, right? The same size, I mean, they are not spherical. If they are having some oblong shape or something else, then aspect ratio will come into picture. If there is relative acceleration between the phases, then virtual mass will come into the picture. If there is heat transfer between the phases, then that will come into the picture. Similarly, phase transfer. And then wall lubrication means if your bubble is approaching the wall, how it should react, whether there should be some what you can say repulsive force that is there. So that, and turbulent dispersion will be how your bubble or your dispersed phase reacts with the turbulent eddies. So all these things have to be modeled, and those are accounted for in this phase properties file.
Hello, sir. This diameter in this pure isothermal phase model, like it's calculated based on the model, or it is some geometric property?
No, that is geometric property. That is something that you have to specify. Say like in fluidized bed, that will be the diameter of your solid particles. In this water and air system, generally, then you have to see say if you are, as sir gave an example, right, wherein you are passing air from some perforator or something, then by experiments or by maybe from the perforator size, you will know what is the average size of those particles. So that will be your input parameter. So that is a parameter that is input that is used by the model to calculate the various forces like drag, lift, and all those things.
So here, water diameter 1 means what? Like what does that exactly mean?
See, because water is a what you can say water is your continuous phase.
Right.
So its diameter will not matter. So you are giving
Okay.
some, and the thing is, in all these things, these are placeholders. So you cannot what you can say not write anything over there. If you don't write, it will throw an error. So you have to give some value. Say large value is also fine.
Okay. Okay. So, but in air, we are mentioning the diameter of the bubble.
Yeah. For air, we are mentioning the diameter. In this case, I have mentioned 0.3. If you will see, what you can also try doing is change these values like of the diameter and see what happens. If you reduce this to say very low, like say in microns, then you see that the whole bubble that we have initially given, it is a whole lump, right? While going up, it diffuses.
Okay.
Something like that you will also see. So that is possible for you to do.
Okay, I understand. Thank you, sir.
Okay. So now going
Hello.
back to the set fields, Dick. Yes, somebody is saying something.
Uh, so we are using this multi-phase Euler form solver.
Yes.
As far as I know, it is used for compressible flows.
Yes.
So, and our flow, I think it is incompressible.
Okay.
So
No,
can
this will
we?
work for both, I think.
Okay. So, okay, if it is incompressible, then we will not be taking heat equation into consideration, right?
Okay.
Yeah.
I'm not
So
sure about that.
John, can I just join in?
Yes, please.
Yeah. So the if it is a compressible flow, so that means in that condition, if either the primary phase or the dispersed phase density is a variation of pressure, then that means that needs to be defined in the fluid system itself. Because both the dispersed phase and the continuous phase, they are primarily fluid, right? Whether it is air or water, it does not matter. They are fluid. And how is
Yes.
that fluid's thermophysical property? Whether the density is kept as constant, or if it is not, then how it is kept as a function of pressure. That needs to be defined. That's
Okay.
one point. The second point is, if it is a compressible flow, then there are source terms to be appropriately, it will change also for a compressible flow system. That's it.
So if I want to use this solver for incompressible flows, then I will not take into consideration the variation of density, and I will give it as a constant. So it will work fine with incompressible also.
Yes. Yes.
Okay. Thank you.
In this case, what Mr. John has showed, he has just taken water and he has just air bubble. Air bubble changes its shape. I mean, not in the Eulerian context. Like say, if you physically imagine this is like a bubble or a region of bubbles, collection of bubbles, and then their bubbles will change their shape and size. The pressure inside the bubble is changing. All this, there is a pressure drop happening. All that is there, but still we are saying density is fixed. We are imposing that it is an incompressible system because we are not talking about very high speeds. Typically in a contactor, let's say
Right.
bubble column contactor. Bubble column is something where a gas is passed into a liquid. The gas velocity would be the
Right.
order of only few centimeters per second. It could be just 10 centimeters per second, 20 centimeters per second. That's a very high velocity. 20 centimeters per second of gas sparged into a liquid is actually very high velocity for that system. So that means for all practical purpose also it will remain as only incompressible flow. So the fluid would be like not a constant
Right.
density, it's only an incompressible flow system.
Okay.
Yeah,
So
Mr. John,
this
carry on.
Yeah.
solver used for liquid.
Yeah, what is your question?
So this liquid systems, right?
I am not able to hear you, but I am assuming you are asking whether can you do for liquid.
Hello.
Yeah. So you can do for liquid
Right.
also. You have to just use the next to fluid as also a liquid. That's it. Instead of air, if you give it as oil, kerosene, then it will be a liquid system.
Okay. Okay. So thank you.
So quickly, I will show you what you need to change to do that, right? So this region adds one bubble. So I will copy it and do that again. So what I'm doing is, with this, I'm adding one more bubble. Okay. But now I need to just edit the location. So first bubble was 4 mm from the bottom and had a diameter of 2 mm. I will keep it 4 mm from the bottom and make it say, sorry, radius as 1 mm. So diameter is 2. Here, maybe I'll make this as 6. So I'll increase its height and then give it a radius of 1. So now we have two bubbles. So it was as simple as that. So we had to run this command, or we have to copy this command so that it is done twice. So at the top it will create one bubble, at the bottom another. So just these two changes, and the heights will be different. X coordinate will remain the same. The Y coordinates will be different, having a radius of 1. I think I need to reduce this because 4 plus 1 and 6, so they will be touching otherwise. Let me make this 3. So I've saved this. I'll just rerun this simulation now. So before rerunning, remember you have to clean the case. So I've cleaned the case. And now again, to run, I have to type block mesh, then set fields, and then decompose path, MPI run. So let's see what we get. So you all can try doing this. I think now by now you should be a little bit more confident in trying to edit this. So maybe after the workshop you all can try and do a little bit more hands-on. Next, after this, what we'll be simulating is we'll be simulating our the next second case, that is fluidized bed. So now fluidized bed, what I've done is I've copied from the tutorial case itself. So you can also copy the same thing, but I've added the decomposed pardic from the previous dictionary to here. So I think I will quickly just compress it and send it to you so that you can also run it. I've compressed it and I will share it with you all. Okay, so I will add. So in the meantime, you all can download and extract this. So I've just shared fluidizedbed.zip. Okay, the simulation is done. So let me reconstruct it. So don't forget to reconstruct. So reconstruct and then parafoam. So here, if I go and look at the phase fraction of air, I see now that there are two bubbles. As they are going up, they are merging. Okay, I could have kept one. I could have increased the distance so that merging would have been a little, what you can say, delayed, but it is merging very quickly here. Let me try and do that. In the meantime, can anybody guess why the bubbles are merging? The top bubble is merging with the bottom bubble. I will make this 8. So why do you think the bubbles merged when both we are leaving at the same time? They should both go and reach top one after the other. Then why are we seeing this bubble merging? Yes, correct. So Arpita is saying because of the wake created by the first bubble, second bubble accelerates. Let me just see. Yes, correct. This is called as wake entrainment. So the first bubble's wake, there will be like a low pressure region. This is something like a slipstream, right? So if you drive behind a vehicle, right, and if you go very close to it, it can actually suck you. So there is a low pressure region. That's why they say that whenever a train is crossing, don't stand very close to the platform. So because there will be a low pressure region that will be created between, and that can suck you. So that is kind of what is happening over here. So the wake behind the wake region of the first bubble is what kind of accelerates the second bubble and pulls it and sucks it. So that is called as wake entrainment. Okay. So I hope you have copied the fluidized bed case and extracted it to your run directory. So please do that. Okay. I will reconstruct and then I will oh, I think I gave too large a distance. So you all can try playing around with this, and if you see that if you give the right distance, then the first bubble will suck the second bubble. Now let us go to the fluidized bed case. I will quickly talk about the fluidized bed case, the setup. So in this case, what we have is let me go to the block mesh deck. So here again we have a very simple geometry, right? We have a vertical column in which at the bottom we have inlet, at the top we have an outlet, then the sides are walls, and the front and back is empty. So very simple geometry. Okay, that is a vertical column with inlet at the bottom, outlet at the top, and sides are walls. Okay. Now in this, what we are going to do is, in this we are going to let me go to the U air velocity. Sorry. We are going to arch air, as sir has said. Okay, so initially that channel will be filled with particles at the bottom. Then we'll arch air. So to simulate this, what we need to do is at the inlet we need to specify something called as an interstitial inlet velocity. So something like an average, what you can say, an average velocity of the flow. So this boundary condition makes sure that we are getting an average velocity of 0.25 meters per second in the y direction or upward direction. Then that is our inlet boundary condition. At the outlet, we are calling it as a pressure inlet outlet velocity. Now, because we have specified the pressure at the outlet. So pressure at the outlet we have specified as, let me go ahead and open that. So at the inlet, we have given a fixed flux pressure. That means the pressure is computed from the velocity field. And at the outlet, we are giving a PRGH pressure. Now, this fixed flux pressure also will adjust the gradients that are there based on the body forces like gravity and surface tension. So it takes all those things into account. That's why we give the fixed flux pressure at both at the walls and the inlet as well. Now, if you see your velocity, at the velocity, we are specifying an inlet. At the outlet, we are giving a pressure inlet outlet velocity. So what it will do is at the outlet, it will give a zero gradient. And if there is some inlet, it will calculate the inlet velocity based on the flux that is there at the wall. So that is what this boundary condition does. At the walls, we have given a no slip boundary condition. The front and back are empty. So this is for our air and particles. Sorry, I discussed only for air and the particles. So for the particles, we see internally, we are initializing them to be 0. At the inlet, outlet and walls, we are giving 0. That means what we are saying is the particle will not cross the inlet or the outlet. They will only remain in the domain, and the walls have been given no slip boundary condition. This is what has been imposed. Now, there are additional temperature files, okay, that are there, in which the temperature has been given as 300 throughout, okay. At the outlet, inlet, outlet boundary condition. So this boundary condition has an outflow, but also allows for some amount of inflow or reverse flow. And if there is an inflow or reverse flow, it will happen with a temperature of 300. Inlet, whatever the air is coming, will have a temperature of 300, and the walls will be 0 gradient. So these are pretty straightforward boundary conditions. Let us go to PRGH. Now in PRGH, at the inlet, we have the fixed flux pressure. Okay. At the outlet, PRGH, I think I discussed this. Yeah. Outlet is where we are specifying the pressure. Inlet, we are calculating the pressure. And the walls also, we are calculating the pressure. Now, these are some default, or you can say turbulence files. Now, if you look at, there is also one file. So you will understand that when I go here. So let me go to the constant and go to the phase properties. Phase properties is what is needed, right? Before phase properties, let us go to thermophysical properties. So in the thermophysical properties, what we are mentioning what is the what you can say properties like Cp, Cv, mu, all those things. So here for equation, we are considering it to be a perfect gas. This is for air. For the particles, you see in this case, what they have considered is they have considered these particles to be glass beads, okay, having density of 2500. Okay. So this is what we have specified. Now, if you see, we have also something called as momentum transport. So for air, we are considering the simulation to be laminar. But if you see the momentum transport file for the particles, their properties are basically calculated based on something called as the kinetic theory for this granular flow. So based on the kinetic theory for granular flow, these properties are calculated based on all these models that are available, the Gidosper model. Okay. You can have a look at them and see how it is being calculated. So now to calculate these properties, we need to specify the temperature for this field, right? That is done in this zero folder. That is the theta for the particles. Okay. So so this is what we are going to specify. Now this value, this is called as a granular temperature. So granular temperature is something that will be calculated. We are just giving some initialization. So normally we generally initialize it uniformly 0 throughout, but some small amount of reference, or you can say small values has been added so that we want to avoid division by 0. So this value, a very small value is being added to avoid division by 0. So all these things are needed. Now let us go to the phase properties. So phase properties is the main thing. So if you see over here, we have two phases, particles and air. Okay. The particles again are constant diameter. So here you see they are sizes 0.3 mm. So they are considered to be 0.3 mm in size. And we are giving something called as a maximum packing factor, right? So that is 0.62. So if the glass beads kind of they are even very close to each other, they are settled, they will not occupy the whole volume. The maximum volume that they can occupy is 0.62. Okay. Now for air, we are considering that to be the continuous phase. So its diameter, we are keeping it as 1. Now in this case, blending is not needed because our continuous phase is always constant air. It cannot be the other way around. Okay, so that's why there is blending is not there, and we have given continuous phase as air. Surface tension we have neglected. Now aspect ratio, if we have not given, that means the diameter is constant. Now we have given the drag. So the drag coefficient for this is Gidosper origin value. You can go and search for this. So this accounts for the packing factor and all those things. Now here we have given a virtual mass force and a heat transfer. So in this case, the heat transfer between the solid particles and air is modeled by the Rance-Marshall model. So if you want, you can search for that model, and you will get details of that. So similarly, how we have done for the previous one, you can go and search. That version. Let me open the C file. So here you see whatever is the, what you can say, Nusselt number will be calculated based on the RE and PR. So Nusselt number is calculated based on the RE and PR. So RE and PR. So for this, the size of the particles will be needed. So in this case, what I can remember is the heat transfer within the solid is not modeled, only from the solid, whatever heat is being transferred to the fluid, that is modeled. So if you need more information about this, you can read in the literature about the Rans-Marshall model. Okay, now, yes, where was it? So again, phase transfer, wall lubrication, all those things we are not considering. Now to run this, again, I have added the decomposed product. So what you need to do is go to your fluidized bed. I've already opened that in the terminal. Yes, type block mesh and then set fields. Okay, I should have showed the set fields for this. So in the set fields is where we are saying that initially half of the domain is like here, if you see, we have divided. So previously we could say that half of the domain is complete air, right? So we would give air as 1 and particle as say 0. But in this case, even though all the particles are settled at the bottom, they will not occupy the complete volume, right? So what is the maximum volume that they can occupy? 0.63. So we have given a volume that is slightly lesser than that, 0.55 for the particles, and the remaining 1 minus that should be given to the air. So in this region, that is at the bottom half, we are defining that 0.45% of the volume is air and 0.55% of the volume is particles. So this is our initial condition, and rest of the places, it is complete air and particles are 0. So this is what we are giving. So now let us, we have run the block mesh. Now let us run set fields. And then after set fields is decompose. So we have to run decompose path and then MPI run. So we are having the same solver, so you can run the same command. If you just press the up arrow key, you will get the command. So it is running. This will take some time to run. This will take around 4 to 5 minutes to run. In the meantime, let me add some. What blending model should I consider in this case? In this case, there is no blending because it is already, what you can say, or I mean, I think so. Maybe the question is something else.
Hello, excuse me.
Yes.
Okay, so I want to ask about this decomposed particle file. So can we copy
Okay.
this file to any of the tutorial case and make it to run parallel? Is it possible?
Yes. Just 1 minute. Thank you, sir. Thank you. So does anyone have any other further question for Professor Naren? He's about to leave now.
So what this last Harsh Patel, Mr. Harsh is asking, does this model consider actual spherical diameter or just a continuum model with porosity? No, we are not talking about porosity of the particle. Porosity of the particle is something, the space which is inside a particle. What we are talking as the voidage or holdup is actually the space outside the particle. That's one. And in the model equation, I'm not talking open form answers or something like that. It is nothing to do with the CFD software. The mathematical equation, if you see the drag force, lift force, Reynolds number, everywhere else, the linear dimension diameter is on an equivalent spherical diameter. So model is developed assuming bubbles and particles are spherical in nature. So I hope, Mr. Harsh, I have answered your question.
Okay. Thank you so much, sir. Thank you.
So if there is anything else later on, I think people can still write, and otherwise, thanks to all. Yeah.
Okay. I will tell them to, if there is something to write to us or maybe to email to you, sir.
Yeah. Thank you.
Okay. Thank you so
Bye.
much.
Yeah.
Thank you. Bye. Yes. So to answer your question, this decomposed paradigm now is universal. Okay. You can just pick up this decomposed paradigm, add it into any, what you can say, any of your simulation, just change. So because this method that we have written is a Swatch method, it will automatically decompose your domain into whatever. You don't have to specify in X number, I want this, in the X direction, I want so many divisions. In the Y, I want, say, like we had done in the first case, right? On the first time when you use decomposed particle, I think when Harish showed it to you. So that time you have to specify that there should be two divisions, say in the X direction, one in the Y and zero in the Z or whatever. Hmm? So that the multiplication has to be always equal to the number of processes that you have. In this case, you just change the value over there, right? In the decomposed particle, whatever you have. So if you have 8 cores, put 8 and then use this in whichever simulation that you want.
Okay,
So that
understood.
works. Yeah.
Yeah, thank you so much.
Yeah, and also the residual files that were provided to you, right? They will also work. Only thing is, in the residual file, if you open, you have to mention what variables residual you have to monitor. Like say in the case where I demonstrated addition of a scalar, the same residual file will work over there. But when you add over there, in that residual file, you have to mention the scalar. Say in our case, we had written scalar 1, scalar 2, scalar 3. So you can add them, and those residuals will also be monitored. Okay. So I hope the simulation is done, but it's still running. So that's the good thing. Whatever you are learning from this, you can copy these files, try incorporating it, using it for your own case. So all
Sir,
these
I have a
things,
question.
yes.
Sir, actually, if we wanted to simulate it as a 2D axisymmetry case,
Simulate what?
sir, this bubble race case that we are running in
Yes.
a axisymmetric condition.
Okay. Okay.
Sir, how can we assign the value of the vertices, or how can we divide the domain?
Okay. So for that, right, we have a tutorial. Is it available in the open form? Let me check. If we have, I don't remember whether we have it on our website or no. But what you can do is you can select a wedge type of geometry. Okay. You can think of it like if you cut a birthday cake, right? How you cut? You cut like a wedge. But in this case, for 2D approximation, the wedge angle will be very small, close to 5 degrees or something, if I remember correctly. Then the two sides of the wedge, you have to give the boundary condition as, I think, cyclic. Okay. Then it will simulate as a 2D axisymmetric case. And that will definitely simplify. Because here we are simulating it as a, what you can say, as a channel, as a slice, as a vertical slice. And that way you can simulate the axisymmetric case.
Okay,
So
sir,
that is
as
possible.
previously we had done a nozzle case. Is that the similar condition?
Correct. Correct. What you did for the nozzle, right? It is exactly the same thing. This nozzle, if you just, what you can say, that z-axis, if you make it, if instead of along the x-axis, if you make it along the z-axis, then you can simulate this and consider that to be like a pipe or something, right? And then give inlet, and then the two patches will be cyclic.
Okay, sir. Thank you,
Exactly. That is what you can do.
sir. Thank you, sir.
So I think our simulation is done. Let me do Terraform. Oh, sorry, I didn't reconstruct. So I need to reconstruct. Now, in this case, what you can say, fluidized bed itself has so many complexities. You can model how the, what you can say, particle is interacting with the wall, right? So it is just, what you can say, a full research field in itself. So if you are interested, you can read literature, and there are different models. Let me do Terraform. Okay. And then alpha.air. So you see now, sorry, I should take alpha dot particles. So at the bottom are my particles, right? As soon as I start to play, air is being purged from the bottom, and these particles start to levitate, and then the air will diffuse in, break these particles up, and then we start to see the fluidized bed in action. It is breaking it up, it is moving up. So we have simulated only for 2 seconds. So this is what you will get. You can try changing the velocity, try changing the amount of particles that are there in the bed. So you have these files, you can try. There are various models. As I told you, you can search also what models are available by just instead of maybe I can demonstrate that to you. I think we have around half an hour. People also wanted me to demonstrate how to add a scalar, right? So what should be done? What should be the one priority? So please tell me whether we should do the scalar transport addition now or you're okay with that. Because in the afternoon session, I don't think so we'll have time. We have around half an hour. Okay, Raghavendra is saying, can you please give a demo with residual file? Okay. Residual file is pretty straightforward, Raghavendra. I will see where I have, if I have a residual file on my system. So I've added a residual file over here. See, the residual file looks something like this. Here you just add which field you want. If you want only U, okay. Yes, the basic at least. Okay, Chaitanya, we can do that quickly. So I'll quickly tell him what needs to be done. So this is the format of a residual file, right? So maybe I can share this with you, or we have already shared it in some session.
Wait,
Okay.
John,
Yes.
just can you open the residual file once again?
Yes.
So whatever variables we define in the zero folders, those should be
Yes.
placed over here in the fields, right?
Not all, not all. I can delete whatever you want to monitor.
But that should be defined in zero folder, correct?
Correct, correct. That should be available. If that is not matching the way it is written, like P should be written like P, like U, whatever the values, that should be written as it is. Like T, if you want to monitor temperature, T. We have added scalar one, so scalar one will be written over here. So as it is written, same way you have to write this over here. Along with this, right, what you need to do is just one more thing, that in your control dict file, right, at the end, right, you have to just add this line, that if you see the line at the bottom, are you able to see that? Function.
Yes.
And then include func residuals. So it will include this residuals file that is placed in your system folder. Just this. So then what it will do, it will start to log this residuals. So when you're solving here, okay, let me open. Sorry, it will create a folder called as post processing. Okay. And in post processing, it now I've added residuals. So folder name residuals will be there. And then if you open that, a DAT file will be there and it will write all those data. Then you can copy this data and you can plot it, or you can use foam monitor that we have demonstrated. So this is pretty straightforward. This is a good way of doing. So with this, what can happen is during runtime itself, you can monitor your residuals, like how we do in Fluent or something, right? You will get plots. Something like that is possible.
Okay.
With this residuals. So only two changes. Here you have to mention this, and in your system folder, you need to add this file. I think this file will be available if you just search residuals in your tutorials. This file will be available in some or the other. Okay.
Okay.
So
There is foam monitor.
Yes, foam monitor is a utility which is already there in your system. Say if I want to run foam monitor over here, what I'll do is I'll just open. See, good way to do will be you go to your post processing, open that folder, and open that folder in the terminal. So you don't have to type the whole path, and just type foam monitor, and then see this -L is to plot it on a log scale. If you don't do that, it will plot it on a linear scale. So remember, this is not -1. It is hyphen and then L, small l, to plot it on the log scale. And then you have to give the name of the file. In this case, residuals.dat. Once you do that, this sort of a GNU plot window will open. So what your simulation is running, you have gone to your residuals folder, you have opened the zero folder, and you have plotted this. This you do it in a new terminal. because in your terminal in which this code is running, that will keep on running.
Okay.
So along with the code, this file will be written again and again, and foam monitor will keep on refreshing this. So you'll see the progress of your simulation and what is happening to your residuals. So if you see in this case, for one of my simulation, the residuals were coming down. So I know that, okay, it is kind of converging, but my pressure is not kind of become stable. So I need to run it for a little bit more longer time. So with this, you can, what you can say, estimate what runtime do you need.
Yes, understood. Thank you.
Okay, yeah, welcome. So, and one more thing that I think Harish pointed it out, that if this command is still running, that GNU plot will keep coming again and again. So you need to do Control C to terminate this command of foam monitor. Yes. So quickly, let me show you what are the steps to edit the. So to edit any solver, first thing what you do is go to your installation, right, wherever you have. So in this case, all we have installed is in OPT, right? For most of you, in OPT you will have OpenFOAM, right? And in that you will have applications. So in applications you will have solvers. So here is where all your solvers are. Okay, if you don't know the path, open your terminal, right, and just type solve. It will show you the part for the solvers. So solvers is in /opt/openfoam9 application and then solvers. So this will give you the path. Now you say, now I will be demonstrating the basic case of the scalar transport form. So I want to edit this, like how I did, right? I created a new scalar transport form. So I will copy this, copy it to say whatever location that I want. In my home, I have the OpenFOAM folder. I will do that in this folder. So because in the other folder I have other things. So let me paste over here. Okay, I have pasted that. And then what you do is you rename this. Important, because this name is already there. You cannot use the same name. So what you do, you rename this, rename it to say scalar transport form for workshop. I have so many scalar transport forms, so I don't know what to name it. I'm just writing this. Open this. So in that one make file will be there, right? In make files will be there, right? So here you need to change the name as well. Okay. If you don't change the name over here, it will compile some other file only. So it is new scalar transport form, and then I have written workshop. Okay. .c, and C is capital over here, and your executable will be created and it will be stored in a app bin, right? But this app bin, whichever is there over here, right? This is not accessible to us. This is this in this app bin, this location, right? Foam underscore app bin is where your default whatever comes with your OpenFOAM, those apps are stored, or those executables are stored. So, but we have another app bin called as user app bin. So it is foam underscore user underscore app bin. So this gets stored in your user app bin. And here it will be stored with the name of scalar transport foam. But now I need to change that name as well. So I will call it scalar transport foam workshop. Okay. And then save it. So these two changes have to be done. Now in options, if you see, these are what are the whatever files will be needed, right, for you to run your case. Uh, Something like maybe like a header files or all these things like finite volume tools, mesh tools, sampling. All these things are the ones that you will need this for your thing. So if you want to know, okay, for my simulation what I will need, the best thing will be open the solver. Like you will know that I want to make this and I want to edit this and I want to make it similar to say like simple form. So you open simple forms options file and see what are the libraries they need. So copy those libraries over here. If you have some additional, it doesn't matter. But if you don't have, then it will throw an error. So this is it. So now after this, the main thing, you have to go to create fields. And before that, this scalar transport form.c, rename that as well. Rename it to scalar transport form workshop. Now, if I open this, we'll go to that again, create fields later. So here you see, here they are saying I am solving for a T equation. Okay, scalar they are calling it as T, but I don't want it to. I don't want to call it T. Say I want to call it something else. I want to call it scalar. Okay, only scalar as of now, or maybe S. So I can write it quickly. Capital S. Capital S is standing for scalar. So here it is saying the DDT, that is a transient term for S, and here diffusion of S, then Laplacian of S, and with that you will need this diffusivity. So I'll change that and I'll say my diffusivity is ds, and then you can add a source by using FE models, or in our case, right, we knew what the source was. So I wanted to add the source something like I want this scalar to decrease in concentration, because this is, say, one of the reactants. So reactants will decrease in concentration as the reaction proceeds. So I will write minus K stands for my rate of reaction. So I can say call it KRR, that is my rate of reaction, times my scalar S. So this is I think somebody was asking that day, right? Implicit formulation and an explicit formulation. So here you see this is an implicit formulation where your source is written in terms of the scalar itself. So this is an implicit formulation. Okay. If you write only a value normal, then your source is written explicitly. Then after this, so here you see I have written S everywhere, but my matrix equation is still called T equation. So that I will change and call it S equation. So this is what I have changed over here, only this. Now, this S equation, you have to relax and then solve. Relax if you are giving some under relaxation or something like that, right? So it will relax and then it will solve those equations. Apply constraints. So constraints are, if you remember, I gave a demonstration for natural convection, right? And there I mentioned that I have applied FE constraints. That means I know if if I'm doing a simulation and I'm running the simulation, say, between two plates, one plate is at, say, 100 degrees, the other plate is at, say, 30 degrees. So my temperature cannot exceed these limits, right, in the domain. It cannot be more than 100, it cannot be less than 30. Unless if I'm putting in from the inlet any cold fluid or something like that. Say if it is a closed domain and if these are my boundary conditions, then it cannot exceed. Then we can add some constraints. So if some constraints are specified, these they take care of it. Now again over here from T, I will change it to S. But this is if you want to add. If you don't want all of this, you can just remove this. Okay, that's it. Only these changes have to be done. Now you will say, okay, I have made changes over here, but how my solver will know what is S, what is DS, what is KRR that I have mentioned, right? So to specify that, you have to specify that in the create fields. So if you see the first step over here, in create fields, you are creating the field for temperature. So I will edit it over here only. I will say create the field for the scalar S. My scalar is a volumetric field, right? Volumetric scalar field. So that is what it is. So volumetric scalar field. The object's name is S. So wherever it was T, I have changed it to S. Now it is reading the U. So because I'm solving the advection term as well, right? So I will need the U. So I will need this. So I cannot remove this. Then transport properties. So this transport properties is read from the transport properties file. Okay. So this line will remain as it is because it is reading transport properties from the transport properties file. But from the transport properties, what it is reading only the diffusivity dt. Okay. So now, instead of dt, I am saying my diffusivity is ds. Okay. And it is a dimension scalar. I will call it ds. Now, if you see, he had also mentioned the dimension over here, right? The keyword ds and the dimension. You can do that, or you can, if you follow this similar case structure, then you whatever dimension you mention in the in your case setup, it will work. So what we are saying over here, that in the transport properties file, look up for ds. and wherever ds is there, that value will be assigned to this variable ds. Okay, then this ds can be used. But if you see, along with that, I have also defined a variable called as krr, or my reaction rate. So I need to create that as well. So I will say, I will copy this, paste it. I think I need to bring it up. Okay, and then I am reading reaction rate krr. I am saying reading reaction rate krr. All this. KRR. Save this. So this is saved. So I'm reading ds krr. I hope now everything we have done. Now once this is done, I just save it. Okay, and then I try to compile it. So to compile it, you need to be in this same folder, right? Where make, create fields, and scalar transport form is there. So you open this in the terminal and then type wclean. Wclean, if you have already compiled previously and you want to change, then you can type wclean and then wmake. And if you have made any mistake, it will point out over here that if you have forgotten something, if you have made any mistake. If it compiles properly, it has compiled properly without any problem. Okay, that means we have compiled our new solver. But how to set up the case? So I will tell you that also, because this new solver is there, but this new solver needs some specific files, right? So what I'll do, I will again open my term. I will go to tutorials and then cd basic, then scalar transport form. Let me do ls. This pitch daily case is there that I want to copy, because I will show you why I need to do that. Nautilus. This is like explorer.exe. So here is my file. Can't do it. Yes. I'm unable to bring it down. Okay. So this is my pitch daily file. I will first copy this. Okay, and then I will go to my, over here, I will go to my run directory. Okay, let me just do this again. I'm opening my run directory over here. Okay. And I will create one new folder so that later on it will be easier for me. I will say demo. In this, I will be pasting it. Now, if you see why I need this folder, because in this folder there is a structure that is there that is designed for scalar transport form. So if I copy these structures, right, this will help me to make my files similar to this. If I copy from somewhere else, the structure may be slightly different and then you might get an error. So it is always good to copy that tutorial file and then add the others. So if you see, if I open, I have a T file and a U file. Okay, U file to whatever you have to add. Then T, I don't need T, right? Instead of this, I will rename it. My scalar is S. Okay. Not only that, inside, if you see, it is written over there. It is written in ASCII format. It is a volume scalar field and object is T. Instead of that, I will change the object to S. Then dimensions. So my scalar is dimensionless. So here is where you can specify the dimensions. If you make mistake here, then it will be a problem. So I have written 0 everywhere because my scalar is dimensionless. Okay. Then let these values be as is. We don't know now. Let's see. Okay. I'm just showing you where to make the changes. Once you do that, you have to go to constant transport properties. So see, in that lookup, it is searching for dt. Okay. Instead of that, now dt, I'm going to call it ds. Now you will say why it is written twice. It is because how in the solver we have looked up for it. If I don't need to write this twice, then I have to mention in quotes ds over there. If I do that, then I don't need to write this twice. So similarly, now diffusivity, the unit is still meter square per second in that equation if you compare. Along with this, I have to write KRR and then KRR. That is my reaction rate. Now, what is the unit of my reaction rate? Reaction rate's unit is 1 upon second. So it will be 0, 0, minus 1, and then 0, 0, 0, 0. And then you mention what is your reaction rate. So because you are specifying your dimension over here, even if you don't specify over there, it's fine. So if I want, I'll give a reaction rate of 1. With this, it will be able to solve. Okay, now I have made changes in 2 places. But is this sufficient? So now in my case file, I have changed 0. In 0, I have changed the scalar. In my constant, I have changed the transport properties. In my system, what I need to change? Control dict, FE scheme, FE solution. Okay. In control dict, I will first change the name of the solver. I'll call it, for lack of a better name. Okay. Then this was it. Save it. Then mainly FB schemes. Okay, because now what you have done is you have specified what is the divergence scheme for your scalar, what is the Laplacian scheme for your scalar with this diffusivity. So if you don't change over here, it will say that divergence scheme is not specified. Okay, Laplacian scheme is not specified. With that error, you can understand, okay, that I have to make changes over here as well. So you need to make changes and you need to specify that, okay, now this I'm just writing, you can use any other scheme as well. And in the Laplacian, you have to make these changes. So this is my diffusivity and this is my scalar. So these are the changes that you need to make in their FV schemes. So what schemes should be used? You are specifying for your scalar. Next, in your solution, you need to specify what solution algorithm that you are going to use, right? So here we have specified solver only for T. Okay. So here I'm going to specify solver for S. So with this, you will understand, okay, in our scalar transport form, we are not solving for velocity. We are only solving for the scalar speed, right? And velocity is our initial condition, and that velocity does not change. That's why we don't need to solve for velocity. So velocity is imported from a previous simulation, and that is used as an initial condition for this simulation. So these are the changes that you need to do. Okay. After you do this, I think you are done. You can run. But I don't know how. Yes.
No, in that file FE solution,
Yes.
the solver name is what is PBI CGS tab?
Okay. What is the full form for this? I think it is something called as biconjugate gradient stabilized pressure. I think is it pressure, Viraj? So if you search for this, right, PBIC tab, it is something like a biconjugate gradient solver which is stabilized. So it has some stabilization also, and what preconditioner you are using. So there are many solvers. Again, if you don't know what solver to use, you can type it is precondition biconjugate gradient and then stabilized. That is the name. So you instead of this, you write banana and then run. It will say, okay, this is not the correct solver. Then it will give you the list of solvers that are available. You can explore each of them and then see which one will suit for your application. Okay.
Okay. So this solver is exactly what, like just like simple form like that. Like this is, I mean, because this
No. These are the linear solvers. How your matrices will be solved.
Okay, but for Gauss linear, something is already written, right? But what is this again? Because somewhere else I have seen Gauss linear. That is
yes. Those are the schemes. Those are the schemes for convection. What will be the scheme, right?
Okay.
For convection, what will be the scheme? For advection, for Laplacian, what will be the scheme? Like this. If you open the scheme over here, right? What will be the scheme for your convection? This is a discretization scheme.
Yeah, I understand.
Okay. To put it more clearly, these are your discretization scheme. How your equations will be discretized. Okay.
Okay.
Then this is how your equations will be solved. What will be the algorithm used for solving? Algorithm basically will be simple only, but the matrix that you get, right? The final matrix that you get, how will you solve that matrix? Okay.
Right.
Depending upon how you solve that matrix, also your solution will run faster, slower, will converge, will not converge, right? If there is
Yeah.
no diagonal dominance or something like that, right, then you have to precondition the matrix so that it runs faster, it converges. So there are a
Okay.
lot of what you can say. This is all into the numerical methods of it.
Okay. So it is like the Jacobi Gauss
Yes, yes,
expression.
something similar to that.
Okay.
Yeah.
Okay. Maybe conjugate
So,
gradient. Okay. Okay.
yes,
Understand.
and the
Okay.
previous one, what you saw, those were your discretization schemes. Say like DDT. DDT will be
Okay.
discretized by your Euler scheme, right? And if you search for Euler, I think first day we had shown you Euler, right? Tn
Right.
plus
Right.
one.
Yeah. Like
Uh,
just like Newton-Raphson, this Euler method is used as
correct,
for
correct.
discretization. Okay. Okay. Fine. Fine. I understand now. Okay. Yeah.
Okay. I think this is it. These are the changes that you need to make. So this was a basic overview as what changes where you need to make, right? I think Swapnil did a very good demonstration. You will get a video. With that, you will understand a little bit more into what advanced what are the advanced techniques to do over there. Like he created some vectors, right? And he calculated the normal gradients and all also. So that was a good demonstration. That video you will have, right? And you can go through it and learn a little bit more.
Okay. Okay. Yeah.
Yeah.
But this is very helpful, sir. Thank you. Thank you very much.
Yeah. Okay. Okay. Thank you. I'm glad that this is helpful.
Yeah.
Okay. I think I'll stop sharing now. If you still have any queries, you can write to us. Okay, you can write to us. We are available.
Any other resources like Raghavendra's
Yeah.
question?
Okay. So Raghavendra, just maybe now I'll quickly rush for lunch and come back. But after I come back from lunch, all the resources that I have, I will share with you. There is one I forget the name. It is a very good resource, right? Also, along with this, what you can do is you can use our own repository, right? In FOSSEE, we have a lot of case studies, right? Where people have already done things like, heated plate, top, heated bottom, then you can look up and then you can see which boundary condition works. Because even in all these resources, they might have given you one tutorial and, what is the way to set it up and all those things. But when you set up for your own specific case, you see that where the struggle lies. So what we have observed is that the struggle lies basically in selecting the appropriate boundary conditions. Why we have only selected a fixed flux pressure or inlet outlet, and why its combination with velocity is one way or the other. So that is where you will struggle a little bit. So there are this our open foam case studies, and we have also uh, what is that called, research migration projects, right? So all those things will be very helpful to you. Okay, you can browse through them. You can read the reports that are available, what boundary conditions those students have used. So they have worked for them. So that is
So
what something
during
that
my
you can.
concluding talk now, I'll show you our website and I'll show you where can you exactly find the resources, and I'll also talk about how can you participate in the project so that you also can gain, you can gain certificates, you can gain knowledge. Okay, so please wait for the concluding talk. I'll be discussing everything. Okay,
Okay.
thanks. Bye bye.